All right, welcome back. So for our second talk today, we have some research that's hot off the presses. The word towards was deleted from the title just in the past week. So we have Max Zeuner who will tell us about a univalent formalization of affine schemes in Cubical Agda.
Yeah, thank you. So this is joint work with Anders Schmedberg, my supervisor. And this is sort of the other side of Cubical Agda. This is not the synthetic topology stuff that Axel was talking about, but this is set level mathematics. And I'll start with a advertisement slide telling you about all the nice stuff that we have in Cubical Agda that makes it so nice as a proof assistant for set level and in particular constructive mathematics. So well, I'll try to keep this brief. So the first thing is that equality is something like paths. So an equality between two objects x and y of a type A is something like a function out of an interval that computes to x and y at the endpoints. And with this, we can even get a notion of dependent paths where we not have one type A, but a line of types B that sort of varies with over the interval. And then we can have elements of B at 0 and an element at B of 1, and we can have a dependent path over that. And we get a notion of transport along paths and dependent paths. So I'm not claiming that you want to have equality as paths if you want to do sort of set level mathematics and univalent foundations, but having a notion of dependent paths that works nicely and the transport along those, this is something that comes in very handy, and we'll actually see this later in the talk. And then the next thing is that we have higher inductive types, and what was used in our formalization project was set quotients and proposition truncations. And those were actually the only ones we needed. And then, of course, we have univalence, and from that, we get a structure identity principle, and I've written it down in this reduced form here. This is a function SIP that takes two commutative rings where you might replace comring with your favorite algebraic structure, and then take an isomorphism of those structures. So in this case, an isomorphism of commutative rings, really just what you would expect from your algebra courses, and you get a path or an equality between those rings. And there's also an important point: everything computes, everything has computational meaning. And although I won't have time to get into details here, there were several points in the formalization where sort of nice computational behavior, especially of the higher inductive types, not so much of the SIP, but especially of the higher inductive type, was crucial to make things work. So yeah, all in all, I would say this makes Cubical Agda nice for univalent formalization of set level constructive mathematics. And I would say this is really in the spirit of Blavatsky's foundational library. And there he did a bunch, so in this paper that I linked here, you can click on it if you look at the slides. He did a bunch of constructive algebra. In particular, he did localization of commutative rings, which are heavily used for schemes. So schemes are, in a sense, a natural continuation of Blavatsky's project. And even if you're not interested in univalent mathematics, they still seem to be an interesting benchmark in general for mathematical libraries of proof assistance. So by now, we have work on schemes in a lot of proof resistance. So the oldest I could dig up was done in Coq in the early 2000s using setoids. Then the Lean MathLib has schemes. There's formalization in Isabel and Hall, and there's one in Unimath. So there are existing formalizations in a univalent proof assistant, but what they all have in common is that they use what I call the Hartshorne approach to schemes, or to affine schemes. And so this is the approach that is taken in the classic textbook by Hartshorne. And this approach is inherently non-constructive. So it not only uses classical reasoning, but also the axiom of choice in a crucial way that cannot be eliminated. And you don't really need any univalence to make this construction work. So if you look at the unimath construction, you don't really need the univalence axiom, but you do need the axiom of choice. What we wanted to do here was formalize a constructive account, and this is sort of the alternative approach to the Hartshorne approach, where you sort of start by defining affine schemes on basis, and then lift everything from there. So we were following a paper by Thierry Coquand, Henri Lombardi, and Peter Schuster, and yeah, when doing this, actually univalence came in very handy and make this whole thing work in the first place. So yeah, here's what this project is about. So this slide is a bit of a mess, but I didn't know how to add sort of breaks that didn't destroy the whole thing. So yeah, follow me here. I hope you can all see my mouse. So what we wanted, the main goal of defining affine schemes is defining the so-called structure sheaf. So this is a functor O going from some ZLR, this is the so-called Zariski lattice, up, because yeah, it's a pre-sheaf, so it's contravariant, into the category of commutative rings. So what is this ZLR? This is the so-called Zariski lattice over some fixed ring R that will be fixed for the rest of the talk. And if you know your algebraic geometry, classic algebraic geometry, you can think of it as the compact open sets of the spectrum of R. So the spectrum of R is the set of prime ideals of our ring, and it has a topology, and you take the compact opens. There's a reason why we sort of have to restrict to compact opens, which I'll get to in a minute. But now prime ideals are not very nice to work with in constructive algebra. So what we do here is we take finitely generated ideals, say A and B of our ring, and we sort of quotient by the relation that we identify two finitely generated ideals if the radicals of those ideals are equal. Doesn't matter too much now what those radicals are, but it's just an equivalence relation, and we can take the quotient. So this is where set quotients come in handy. And the way we define the structure sheaf O is we look at generators of the Zariski lattice, and they are written as D of F, where F is an element in R. So classically, they're these basic opens, prime ideals that do not contain the element F. Constructively, this is just the equivalence class of our principal ideal generated by this one element F. And we map this to this ring. This is called R local. We say R localized away from F, where this ring is the elements of this ring are fractions, where the denominator is a power of F. So we would construct it much the same way you construct the rational numbers from the integers. So this is also some sort of set quotient, but then restrict what the denominators can look like. And so there's a bunch of issues to be tackled in order to make this work. So the first is that we need something like a comparison lemma for distributive lattices, because we're not actually doing topological spaces or locales. Even the Zariski lattice is just a distributive lattice. So in particular, what we're actually doing is we have these generators or basic opens. So I call this BO. This is some poset category. We define a pre-sheaf into com rings first here. Then we have the inclusion into the Zariski lattice. So we want to do Kahn extension to get our structure sheaf here. And then we have to prove this comparison lemma that if we can prove that this guy is a sheaf, then this guy has to be a sheaf as well. But before we can even talk about sheaf just on the pre-sheaf level, there's the issue that for this Kahn extension to exist, we need this guy to be small. So in particular, we had our base ring R lives in some type theoretic universe. So the category of com rings that this ring R lives in will be big, but then sort of ZL has to live in the same universe as R. And without any further axiom, without adding any further axioms to Cubical Agda, like proposition resizing, it's a bit tricky to get the definition right. So what we ended up doing, following a paper by Luis Español, actually defining ZL to be the quotient on the type of list of elements of R. So the list here is supposed to correspond to the generators of a finitely generated ideal, and then we quotient by the relation that identifies any two lists if all elements of one list are in the radical of the ideal generated by the other list, and vice versa. So this is a bit of convoluted way of saying that those two radical ideals are the same, but this is the way to write it if you want to stay within your base universe, because equality of two ideals is something that lives in the next universe in a predicative setting. And then of course there's the big question of, can we actually make this? So now we're just focusing on this construction on basic opens, but can we actually make that work? And there's the question of well-definedness, right? So morally, we would expect something like, well, if d of f equals d of g, then r localized away from f better be equal to r localized away from g to make this construction work. So without univalence, we don't really have any hope of proving such a statement. With univalence, we can actually prove that, but here's the catch: this is actually not enough, and the reason is kind of subtle. So if we look at what basic opens generators are in univalent foundations, well, they're a subset of the Zariski lattice, right? So what is a subset of something? Well, this is a function from, in our case, the Zariski lattice into the universe of homotopy propositions. So for each element in ZL, we assign a proposition, and if this proposition is true, that means that element is a basic open, and if not, then not, right? And in this particular case, we need this high inductive type called proposition truncation, and this causes some trouble. So let's look at what this OB actually looks like. Well, it goes from the type, or I mean, this is a poset category of all the ZLs such that, of all the A's in ZL such that A is actually a basic open into Comrian. And what does it mean to actually be a basic open? Well, there has to exist an F in R such that D of F is just equal to A. And this exists here is sometimes called mere existence, and it is defined using proposition truncation. So what it does is it sort of hides the content. We might know that some A is a basic open, but we're not explicitly given an F for which A is just D of F. But if we are given an F and a proof P that D of F equals A, well, then we know what OB should do, right? So you see these bars here, those are canonical elements of this mere existence type, saying, well, if we have an F and a proof that D of F equals A, well, then we get a proof for this existence statement. And if in that case, we know what OB should map this guy to, well, just R localized away from F, right? And the question is, does this define a function? And this is actually a hard problem, because it's very hard to define maps out of proposition truncations when the goal type is not a proposition. And in our case, it's actually a groupoid. So it's not even a set. Essentially, because of univalence, the category of commutative rings is a groupoid. So if it was a set, well, then our naive well-definedness statement would actually be enough. If we had a G and a Q, sort of an alternative G and a Q that A also equals D of G, well, then D of F and D of G have to be equal. They're both equal to A. And we know that those two rings are equal, and sort of this would be a well-defined map. Since this is a groupoid, that is not enough. We have to check some further coherence, some condition on the equality that we get between those two rings here. And even if you're not that familiar with univalent foundations, you might have seen this coming, because if you look at a classic textbook, such as Grothendieck's, or any other algebraic geometry textbook, pretty much that is not Hartshorne. They also is something, well, if d of f equals d of g, then there's a canonical isomorphism between those two localizations. So somehow there has always been this notion, so people were aware that it's not enough to make this well-defined, but just saying, well, there's some isomorphism, as canonicity plays a role here, right? And well, here the problem becomes really clear. We can actually sort of flesh out what canonicity has to be in this instance to make the construction work. So here's how we managed to solve this issue. Well, the observation is that the structure sheaf does not actually only take values in commutative rings, it takes values in R algebras over our base ring R. And this is because localizations are R algebra, or localization away from F. At some point, F is an R algebra in a canonical way. And when you do some standard commutative algebra to say, well, if you have d of f and there is less than d of g, so this is an inequality in our formal Zariski lattice that is a poset. You might just think of this as set inclusion if you're more comfortable with it. Then by some standard commutative algebra, this means that this radical ideal is included in this radical ideal. In the formal lattice, this almost holds by definition. And this is the case if and only if G is a unit in the ring R localized away from F. And this in turn lets us apply the universal property telling us of localization, telling us that there has to be a unique ring morphism phi from R localized away from G to R localized away from F, such that phi sort of commutes with this division by one morphism, which for any localization, right, you can take an element x in R and you get a fraction by dividing by x. So this is a way of representing elements of R in localization. And it is this morphism that actually makes localizations into R algebras. So what this actually says is that there's only one R algebra morphism between our two localizations. Or to put it in a more univalent fashion, the type of R algebra morphisms between R localized away from G to R localized away from F is contractible. And if we combine that with the SIP for R algebras, this tells us if we have a path between D of F and D of G, then the type of paths between R localized away from F and R localized away from G is contractible. And I guess this should also go in the other direction, but it's not strictly needed. And we can also, small remark, what is the center of contraction? What is the unique path here? Well, this is just the SIP applied to the unique iso you get from those. So canonical iso means it's actually an isomorphism of R algebras and is unique there in this category, right? So this iso you get because inequality here gives you both inequalities here, so you have one morphism going in each direction, so they have to be mutually inverse. And so now we can, if we go back, right, we have to apply the theory of proposition truncation and see how we can map from a proposition truncation into a groupoid. Well, if you spell it out for our case, using this result by Nikolai Krauss. So Nikolai Krauss sort of classified maps out of proposition truncations into arbitrary or types of arbitrary H level, but you have to sort of give the H level of the codomain explicitly. Well, in our case, we have a groupoid. So what we have to do is, given three elements F, G, and H, such that they are all equal, we have to provide a filler of this square. So this is not a, so now things get really cubical. So this is not a diagram in R algebras or rings. This is really a square, so one of these basic entities of cubical Agda or cubical type theory. And these are not maps, these are paths, right? So we have this SIP applied to this isomorphism here that we get from this path. And this path up here we get from here, and then of course this we get from composition here. And yeah, you have two interval variables, I and j. So the filler of this square is some term that takes two variables, interval variables I and j, spits out an R algebra such that if we set I and j to 0 or 1 respectively, we sort of end up on one of those boundaries. But it's actually not hard to provide a filler of this square, because if you know your cubical type theory, this diagram will look very familiar to you. This is how you define composition of or transitivity of equality, the path composition. So giving a filler of this square is equivalent to giving a path between this path and the composition of these two paths. And what we said, this is the center of contraction of paths from here to here. So we're done. How much time do we have left? Oh, that's great. And so we can carry out this construction. I didn't say anything about the morphisms because we wanted to define a pre-sheaf, right? I just told you how to do the construction on objects, but this contractibility of Hom types actually also gives you restriction morphisms for free, essentially. And now what is left is proving that this construction, this OB, is a sheaf. And what I'm going to look at is the case where we have one basic open D of H covered by two others, D of F and D of G. And I didn't really tell you what a sheaf on the basis of a distributive lattice is in our formalization, but I'm going to tell you what it unfolds to essentially in this reduced setting. Well, what we have to prove is that this outer square is a pullback square. So because D of H is the join of those two, it is in particular bigger than D of F and D of G, right? So we have restriction maps from here and down to here. And then we have this guy here. This is R localized away from the product of F and G. What this is actually the structure sheaf evaluated on the meet of D of F and D of G. And this actually, in our formalization, computes to this very R algebra by Raffel. So yeah, this is what we have to prove to be a pullback square. And the way this is done in the textbooks is we have some general lemma, which I'm also gonna rewrite in a pullback version for two elements. So given any R algebra A and two elements F and G, such that together they generate the whole ring, so every element in A is a linear combination of F and G, then the following is a pullback square. We go from A to A localized away from G, and A to localized away, and then localized away from the product. So yeah. Then this is a pullback square. Note that, of course, this F and this F doesn't have to be the same, but now we can apply our lemma, but with the following observation. Well, if D of H is sort of covered by D of F and D of G, that means that F and G, seen as elements and are localized away from H, generate the whole ring as an ideal. And so we plug in our localized away from H as our A, and we get this square as a pullback square. So this is a double localization, right? We first localize away from H and then away from F, and this is a bit of abuse notation because of course we localize away from F divided by 1, but yeah, you get what I mean. So how are those two squares related? Well, actually, all the vertices are equal. So of course these are equal, but let's look at one of the more trickier cases. There's a general statement telling you that this sort of double localization is just localization away from the product. And because essentially of this relation about the D's, so we can drop the h here. So composing those two equalities gives us a path here and similar here and here. But so what we want, we know that this is a pullback. We want that this is a pullback. It's not enough to know that those are all equal. We have to give dependent paths. Sort of, if we go along those equalities, right, we want that this morphism becomes just this morphism. We have to give a dependent path over those equalities. And if you work in a non-univalent setting, these diagonals won't be equalities, they will just be isomorphisms, right? So you might be able to proceed by saying something like going down here, then here, and back up via the inverse of this morphism, gives you this, or like all these squares commute. But sort of with dependent paths, we can reformulate this commuting property, and we actually get these dependent paths for free, because we already said, right, there's only one such morphism between any two of those guys, and yeah, essentially the right relations about the d's hold, which they do in this case. So then we can use some cubical machinery. Say if we have a type line, which will be morphisms from here to here, somewhere on the diagonal, and the endpoint is contractible, then whatever we put in here we'll get a dependent path over to here, to the center of contraction here, right? And yeah, then we have a path on vertices, a dependent path between edges, so we can transport any properties of this square to get the property of this square, and we do that for the property of being a pullback. And so this was all done in R algebra, so you might think, okay, what about comrings though, right? But because in the end we want the structure sheaf to be valid in comrings. Well, we said we got the yeah, maybe I skipped that one. Let me go back. Yeah, so okay, we said it actually takes values in R algebras, but we get it as a function to comrings by composing with the forgetful functor here, right? So yeah, since the forgetful functor preserves limits, it also preserves pullbacks, and we get a pullback square of the right shape in the category of comrings. And that is how we prove the sheaf property, albeit in a more generalized setting. So yeah, summing up, I presented just the outline, of course, of our formalization of affine schemes, and I'd say the interesting points being, well, we use a point-free constructive Zariski lattice, but otherwise this textbook strategy, sending d of f to r localized away from f, is really followed. But yeah, we can elaborate on why it actually works, or why it is well defined in our setting. And yeah, the way we proceeded was having a simple algebraic observation about localization as R algebras and contractibility of certain types, and that let us use univalence to make this construction work out of the box in a sense. We can, the way this is done in the library, that there is a very general way of constructing pre-sheaves by just assuming contractibility of certain Hom types, and yeah, and also very helpful transport lemmas to prove the sheaf property. So this is really abstracted away from because we only have to show that, yeah, certain types are contractible and everything else works. And so for the future, we hope that we get a definition of schemes, not only affine schemes, and the constructive notion we want to aim for is that of the spectral scheme, and this will be a ringed lattice, so a lattice with a sheaf of commutative rings. And what would be very interesting, I think, just to see formalized, is that assuming classical axioms, what you get is actually just quasi-compact, quasi-separated schemes. So this is a very general class of schemes for the classical algebraic geometry. And some might argue actually general enough to do algebraic geometry. And in particular, one example, subclass of these quasi-compact, quasi-separated schemes or projective schemes. So that'd be very nice to have formalized as well. Yeah, that's all I have to say. Thank you.
All right. Thank you, Max. And are there any questions, comments? Just feel free to unmute yourself. Egbert, yeah.
Okay. Yeah, thank you for the very nice presentation. I think my main question is about the section of well-definedness of the map of the structure sheaf. And there I thought the argument would go entirely different, but you didn't do it that way. So I'm going to ask you what you think of the entirely different idea. So you have this map that sends F to R localized away from F, and this define okay. So you can view R as a posets where the F is less than G if D of F is contained in D of G.
Yeah.
And then the basic opens, they are just the poset reflection of this poset. And we already have a pre-sheaf on it, namely the map that sends F to R localized away from F. So all that should be done to do the well-definedness is to say, okay, this poset reflection, actually, it's also a rest completion, and therefore you can map into any category, and then you're done, right? Shouldn't you be done? Because now, once you recognize that the universal way to turn a pre-order into a poset, so that kind of makes it univalent.
Yeah.
Is kind of is a very limited version of rest completion, where categories have only one morphism between any two objects. So I think this part can be simplified a lot.
Yeah, I mean, I'm not claiming that this is the only way to make this construction work.
You showed how you did it. It's very good.
There's for example, another suggestion I got was that, well, localizations are actually com rings with an epimorphism from R, and
sure. Yeah.
this is a set, right? So then we map from proposition truncation into some sort of subclass of com rings that is a set.
Yeah.
And then this is actually enough. So yeah, there are definitely different ways of doing this.
Yeah. Okay. And okay, so now
yeah, maybe I'm gonna say, I don't know if this is harder than what you said, or like in any case you have to show something, right? In this case,
no, I don't think
you show
so.
this, and then you get this for free essentially, right? I mean, this is stuff that was just in the library.
Oh, okay. Well, if it was already in the library, then it was okay.
Yeah, exactly. I mean, we don't have a lot of stuff on posets, yeah, or anything on the rest, or maybe we do actually. But now, yeah, these things change kind of quickly, and sometimes you just go with what is in the library, I guess.
Okay, so and my last question maybe is more philosophical question. Are you not bothered by the fact that you only do a sheaf condition for finite covers, whereas in a textbook it's for arbitrary covers?
Yeah, I mean, so I asked this question to people that know more algebraic geometry than me. It's like, shouldn't we be bothered? And sort of the justification of, oh, sorry, I had some. Wait. Yeah, the justification is that, well, once you just carry on, you don't stop at affine schemes, but you do what they call spectral schemes with ring lattices. You actually get quasi-compact, quasi-separated schemes. You can recover them, and then it's like
you get the same category of schemes.
Yeah.
But you already got that category of schemes once you were on the basis. Like the
can you? I'm not sure.
the sheaf on the basic opens. That category is already the same as the category of sheaves on all opens in the Zariski topology.
Right, because I guess extensions
So
are
you get
uniquely determined.
The point is just you get equivalent categories of schemes anyway. It's just how much do you show about it? Anyway, thank you. Very nice talk.
Yeah, I'd be happy to discuss this more.
Yeah.
I have a question. Again, very nice talk. I think this is great work. Can you go back to slide 4? Right. Yeah. So you, in the upper left, you took the finitely generated ideals and then you did a set quotient to identify the ones with the same radical. Is there a reason you couldn't take the radical ideals? You know, just
yeah.
take...
So I mean, this is, I guess, related to Egbert's question, whether you'd be bothered by that, whether you want radical ideal. Because if you drop the finitely generatedness here, then well, you actually just get spec of R, right? For something that is isomorphic to spec of R. Well, one reason is that, okay, cubical Agda is predicative, right? We don't have any resizing axioms. So the type of ideals of the ring, and that's also the type of finitely generated ideals, they live in the next bigger universe, right? So we can't do the Kahn extension stuff here. And the reason we did finitely generated is that we can actually then make this small by just looking at lists of generators.
Yeah, so I wasn't worrying about finitely generated or not finitely generated. I was wondering about, instead of quotienting ideals based on having equal radicals, just limit to the ideals that are radical. They're equal to their own radical. And then you don't need to set quotient.
Right. That's true, but it would still be a big type, right?
Yeah, so maybe the issue is, instead what you do is you present the ideals and then are able to put a small...
Yeah, exactly. So I've been a bit sneaky here, just being like very suggestive to motivate the actual construction used here later, right?
Yeah, okay. So
I guess fair enough.
Yeah, maybe there's not a way to just characterize the... well, I still think, couldn't you take lists of generators that have the property that... Oh no, see, I'd want to say anything in the ideal is in the radical.
I mean, these things are... The nasty thing is, right, that the radical of a finitely generated ideal doesn't have to be finitely generated, I guess.
Yeah, okay, so so that answers my question. I really now see what you're doing. Good, thank you.
Well, thanks.
Okay. Anyone else? Okay, well, thank you again, Max. And
I can